The topic of 9.2 is pair the samples for two means. Pair two samples for two means. Let me tell you that from the texts, they are a little bit hard, but after the examples, you will know. Wow, it's easier. It's easier. Okay, let's start from now here. Are two populations the same? Is the average height for men taller than the average height for women? Is the mean weight less than a diet than before? What does it mean? If $1 have a diet and my weight should be less than before, but that's $1. But if we have 50 people or 100 people, we have on the plain diet, and we lose our body weight. Do we have any scientific evidence to support our view? Okay, you can compare populations by comparing their means. You take a sample from each population and compare the statistics. Anytime you compare two populations, you need to know if the samples are independent or dependent. The formulas you use are different from different types of samples. Okay, if how you choose one sample has no effect on the way you choose on the other way, those two samples are independent. The way to think about it is that independent samples, the individual from one sample, are overall different from the individual from the other sample. Okay. This will mean that sample 1 has not an effect on sample 2. The sample value from the one sample are not related or paired with value from the other sample. But in different situations, if you choose samples so that measurement in one sample is paired with a measurement from the other sample, this time is called dependent or matched or paired I prefer to call it paired. Why? Because 100 people attended the plan or project called drinking black tea and lower your blood pressure. Actually, we cannot see the average of the blood pressure because all 100 people, they are individuals. And we just want to know 100 people, if 90% of them, after drinking enough black tea for a month or 2 months or certain period, they did decrease their blood pressure. How can we have the evidence to show this? Here we can run a pair the sample, pair the t-test, because we want to compare this one or that one. And I have one more example. Students attend, for example, economics. Before they attend the course, after they attend the course, do they show different test scores on the test? And one student before and later is called paired. So if you learn this, you can know the concept how to compare one, especially for human. It's very interesting. And here, often before and after situation, you want to make sure that there is a means for paired data value from one sample with a specific data value from the other sample. One way to think about it is that the independent samples, the individuals from one sample are the same individuals from the other sample. Okay. Though there can be another reason for paired values, makes the value from each sample paired. Okay. Here is an example. Determine if the following are dependent or independent. Randomly choose 5 men and 6 women and compare their heights. Solution: they are independent. Since there are no reason that one value belongs to another, but the individuals are not the same from both samples. The individuals are definitely different. A way to think about this is the knowledge that the man is chosen. One sample does not give another information about any the other woman is chosen. Okay. Second one, choose 10 men and wed them. Give them new wonder diet drug and later wed them again. 10 men, they have new wonder diet drug and later after the treatment or after the treatment of the kind of practice, wed them again. Actually, 10 men are still the 10 men. They are dependent since each person's before weight can be matched with their after weight. The individuals are the same of both samples. One way to think about this is that the knowledge that a person weighs 400 pounds at the beginning will tell you something about their weight after the diet drug. Okay, so it's very easy to distinguish the differences about independent or dependent samples. Let's move to next. And here, to analyze data when they are matched or paired samples called dependent samples, you conduct a paired t-test. Okay, let me slow down here. Paired t-test. Paired t-test. Since the samples are matched, you can find difference between the value of the two random variables. First one, hypothesis test for two sample paired t-test. First, state the random variables and parameters in words. X1, random variable 1. X2, random variable 2. Mean 1, micro 1 or mean 1. Mean of random variable 1. Micro 2 or mu 2. Mean of random variable 2. Second, say the non-hypothesis and alternative hypothesis and the label of significant label. The usually hypothesis will be non-hypothesis. The mu are the same. The alternative hypothesis, they are not the same. Smaller than, greater than, not equal. Okay. However, since you are finding the differences, then you can actually think mu1 minus mu2, that is mu sigma mu d, population mean value of the differences. Population mean of the differences. Okay. So the hypothesis becomes non-hypothesis mu d is 0. H1 mu d is smaller than 0. Mu a mu d greater than 0 or mu d not equal to 0. Also state your alpha label here. Generally 5%. Okay. And 4. Find the sample statistic, case statistic, and p-value. Sample statistic, the difference is d equals x1 minus x2 for each pair. For example, $1 exercise every day. Before I start my exercise plan, my body weight is x1. After I exercise every day or 5 days a week, for a month, my body weight can be x2. Sure, x1, x2, the sequence can be changed according to your definition. Simple mean of the differences d bar equals sigma d divided by n. Standard deviation of the difference is SD equals sigma the square root of d minus d bar. Here n minus 1. Sure, we did the similar. Here should be simple variance, not deviation. Here should be because there is lacking a square root. There is, I think, it's standard variation, not standard deviation. Okay, and n minus 1. Do you remember why? Why here is n minus 1? N minus 1, it means that is from sample, not a population. From the sample, not a population. Okay, next. Number of pairs n. Number of pairs n. And the t-score, t-test score, t equals d bar minus mu d over sd. Then this part is over square root of n. Where degrees of freedom, df, degree of freedom, that is n minus 1, n minus 1. And here, mu d is 0 in most cases. And the command line to calculate p value is this one. And note, if alternative hypothesis mu d is smaller than 0, then lower limit is this one. Upper limit is 1. Okay. Or use R. R is a free software. And this is where you write reject H non-hypothesis, or fail to reject non-hypothesis. The rule is if the p-value is smaller than alpha, reject non-hypothesis. If the p-value greater or equal to alpha, then fail to reject. There is where you interpret in real-world terms in conclusion to the test. The conclusion for a hypothesis test is that you either have enough evidence to show alternative hypothesis is true, or you don't have enough evidence to show alternative hypothesis is true. Confidence interval for differences in means from paired sample t interval. The formula will look like this. Difference x1 minus x2. Same mean of the differences. Number of pairs. And the confidence interval estimate of the differences is this one. D bar minus E smaller than mu D smaller than D bar plus E. And the E is this one. We did a similar work last week. And how to check the assumption of t-test and confidence interval. In order for the t-test or confidence interval to be valid, the assumption of the test must be made, so that whenever you run a t-test or confidence interval, you must make sure that the assumptions are met. So you need to check them. Here is how to do this. For assumption that the sample is a random sample, describe how you took the samples. Make sure your samples technique is random and that the samples were independent. Samples were dependent because they are paired. For the assumption that population of the differences is normal, remember the process of assessing normality from chapter 6. Okay. After a long term, we move to the example 9.2.2. After we finish this example, you will be clear about how to run this one. Example 9.2.2, hypothesis test for paired samples using the formula. A researcher wants to see if a weight loss program is effective. She measures the weight for 6 randomly selected women. Okay. before and after the weight loss program. Check this. Is there evidence that weight loss program is effective? And now, the person number one before there is 165. I think can be pounds. After that, 143. Yeah, it looks significant because the number one lady get rid of 18 pounds. Okay, and the second one before 172, after 151. Wow. Oh, sorry. I miscalculated. The first lady get rid of 22 pounds. The second lady get rid of 21 pounds. The third lady get rid of 25 pounds. The fourth lady get rid of 24 pounds. The number 5, the lady got a loss of 16 pounds, and this one 21 pounds. Personally, it's very significant. State the random variables and parameters in words first. S1, the weight of a woman after the weight loss program. S2, the weight of a woman before the weight loss program. Before, okay. According to the textbook defines X2 is before, X1 is after. Okay, according to definition. And mean one, the mean weight of a woman after weight loss. Mean two, before, the mean weight of a woman before. Okay, and here H is 0. Non-hypothesis mu D is 0. Mu A, mu D smaller than 0. Alpha level 0.05. A random sample of 6 pairs of weights before and after were taken. This was test stated in the problem. Since the women were chosen randomly, B. The population of difference in after and before weights is normally distributed. To see if this is true, look at the histogram, number of outliers, and normal probability plot. If you wish, you can look at the normal probability plot first. If it doesn't look linear, then you may want to look at the histogram and the number of outliers at this point. Okay. And this one, the box plot. There is only one outlier in the differences data set. Outlier is here. Difference, what does it mean? The weight differences in pounds. And here, normal quantile plot of differences in weights. Okay, here, sample statistics from the same. Before, that is here. After, that is here. And now we need to calculate the differences. After minus before. Okay, let me do this. Okay, I'm going to have a new Google Sheet. Example 9.2.2. Okay, and now just copy here. Okay, I move this table to my Google spreadsheet. Okay, and first one, X1, a weight of woman. Oh, sorry, I forgot it. Okay, the first one, we need to calculate before that is S1. So before that is S2. And after that's S1, X1. So the D equals X1 minus X2. And how to calculate X1 minus X2? Here you can click this cell, move to our function, the function location, type equal, and click X2. X1 is here, and click minus, and click here, enter. We got minus 22, and click on this cell. There is a small round symbol on the bottom right corner. When we move our cursor, our mouse close to it, it becomes a cross, and hold the mouse key. Don't release it until here. Okay, we got the similar data here. Minus 22, minus 21, minus 25, minus 24, minus 16, minus 21. So we already have the first information here. Okay, next. The mean and standard deviation are here. The D bar is the average of this one. We can type here. Mean of D. Mean of D. And we can type here and click equal, type average from here and click answer. The average of D is minus 21.5. Minus 21.5. So this one is okay. And next, what is the standard deviation of D? If you forgot the definition, move upward here. Standard deviation of D, like this one, but I think here is a mistake. The author forgot to place a square root symbol here. Okay, then we can here standard deviation, that is equal, click here, STDEV, and we select dot S. It means standard deviation from samples, and the denominator will become n-1. Select here and click enter. Yep, here is the answer. Oh, sorry, here. Yeah, the answer is 3.15. So we can think this one close to 3.15. 3.15. Now we have the basic information here, and that's the test statistic. The test of statistic. The T, that is d bar minus mu D, and standard deviation divided by square root of n. We can rewrite it. D bar, that is 21.5 minus n mu D, that is 0, and standard deviation, that is 3.15, and square root of n, that is square root of 6. Square root of 6. Let me rewrite the formula. The T will be minus 21.5 minus 0, 3.15 divided by n, that is square root of 6. Square root of 6. And if you don't know how to calculate, let me show you. Okay. Minus 21.5 divided by 3.15. And here is a tricky part, because the square root of 6 is in the denominator of the denominator, and now it becomes a numerator times square root of 6, and click OK. Oh, so it's not x, sorry, it's multiplication. Okay, we got the answer. Close to the textbook, minus 16.71. Why it's different from there? I don't know why the error is so big. Not the same one. No, not this one. Okay, I confused why I follow the direction but I didn't get the right answer. Okay. My calculation is minus 16.718, close to 7.2. But here the answer is 16.779. Okay. The p-value, how to calculate the p-value? There are 6 pairs since the degree of freedom, that is n minus 1, that's 5, that's 5. And using this one, got the p-value is 6.87 times 10 to the minus 6. Wow, it's very small, very small, like this one, And since the p-value is smaller than 0.05, reject non-hypothesis. And the conclusion is there is enough evidence to show that the weight loss program is effective. Okay, how about you use your computer and your handwriting to take notes from this one? 3 minutes. And this one will be one of the final exam question. Is it okay? Okay, 3 minutes. Any question, please let me know. Let me choose someone. Okay. Okay. After that, I will introduce you this one. So this Kingdom is a free applications online parity test calculation, calculator dependency test. I'm going to copy it and paste to you. Okay, then tails, two sides. Okay, you can either one side after minus before less than average. Either one is okay. And significant label 0.05. Outliers included effective, medium, and type effective. Okay, we can use this one. Effect size 0.5. Expected differences here, digits here. Before Control C copy and Control V paste. Control C to copy, Control V test. Okay, here. And the p-value is very, very small. Okay, we can check one by one. Sample size 6. Average of differences minus 21.5. We got a similar one here. D bar, the average of differences minus 21.5. Standard deviation of differences, SD, 3.1464. Yeah, very close to 3.15. And the t-value, the t-score is minus 16.779. And here very close. Okay. And sure, we have extra information here, and now this one we don't need that. And the conclusion is, since the p-value is smaller than 0.05, very, very small, and there is enough evidence to reject the non-hypothesis, it means there are strong evidences to show the weight loss program is effective. So is everything okay? Yeah, if no more question, next week I will give you another example like this one, because the parity test is important for everybody. Okay, if no more question, let's meet the next week. See you everyone.